Okay, so let's talk about the number of possible real roots given a polynomial. So down here we have a polynomial, just a big string of terms added together. Notice we have a degree 7 polynomial here because my highest exponent value is a 7. My leading coefficient appears to be positive, but these are just placeholders. Notice they're all capital letters. They're just recognizing that this could be any number, positive or negative, and the rules we're going to talk about will apply. So how many roots will this degree 7 polynomial have? Well, it's going to have 7 roots, right? We talked about that last week or the week before. The number of roots is equal to the degree of the polynomial. So then we talk about the fact that there could be imaginary roots, right? So if you think about your quadratic, if you have a quadratic like this, and it has a vertex that is above the x-axis, that has imaginary roots, so they're not real. They wouldn't actually cross the x-axis. So this would not be a real root. This would actually go over here in this category, right? So an example of something that does have real roots is going to actually cross the x-axis like so. So that would have 2 real roots. So there's quite a few possibilities when you think about a degree 7 polynomial, right? So let's say we have 7, because we know it could cross the entire number of times. That would leave me no non-real roots or irrational roots, right? And when we're talking about these roots, we're thinking about things like we would get over here when we talked about our quadratic. If you have a quadratic that you factor and you get things like this, we know they don't actually have x-intercepts. And those always come in pairs. Think about it, out of the quadratic equation, we get plus or minus every time. So roots like that come in conjugate pairs, we call them, and they are, so it's always that plus or minus version. So then we could have, if we were to have 6 real roots, for example, that would mean we'd have to have 1 non-real root. Well, that's not possible, right? Because we know those come in pairs. So these numbers have to be even over here. So this is going to go up by 2s. 2, 4, right? 6. So this is going to have to go down by 2s. 5, 3, right? And 1. So these are our options. We could have 7 actual intercepts where this thing is going to cross 7 times. 1, 2, 3, 4, 5, 6, and 7, right? So it crosses all 7 times. You could have 5 where one of them's up above. So you have something like this. There's the one, oh, whoa, something weird happened there. So you get a turnaround. Oh no, and now I'm on the eraser. Okay, let's try this again. Okay, so you go up and turn around like this before you come down. Now we have 1, 2, 3, 4, 5 roots, and the imaginary one comes from right up here. If you were to redraw the x-axis so that it went through, it could have crossed here twice, but it didn't. And then the points where it could cross here, it actually did right there and right there as far as number of intercepts. So that one would be 5 intercepts, and so on and so forth. So you could have 3 or 1. You can't have 0 with an odd degree polynomial because think about it. Think about the most basic example, a line. You have to cross the x-axis at some point because the arms face opposite directions. So you can't cross 0 times. But let's think about an even degree polynomial. So our next example, we have a degree 10 polynomial. So degree 10 right here. Degree 10 could have as many as 10, well, it will have 10 roots. It could have as many as 10 real roots or some combination going down. So again, if you think about possible x-intercepts, you could have up to 10 even degree. So this thing is going to have arms facing the same direction. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. That crosses all 10 times. So you could have 10 real roots, which would leave us 0. Notice there aren't any hills or valleys that are off of the x-axis. And again, what I mean by that is if we were to do this type of thing, then we would have these things that weren't counted down here on the x-axis because they're not real roots. So nothing like that is happening over here, so we would have 10 real. Then again, these have to come in pairs, so we know these are going to go up by 2s. 2, 4, 6, 8, all the way up to 10. Why is that possible? Well, think about that. Could we do 10 that were all off? If I were to turn this original one I just showed you over there upside down, I think that's right, and face up, you would have no real roots. It doesn't cross at all because the arms face the same direction. That's possible now. So then going down, we would have 8 real roots if we had 2 non-real roots. We would have 6 real roots if we had 4 non-real roots. 4 real roots if we had 6 non-real roots. 2 real roots if we had 8 non-real roots. And we'd have none, 0, if we had 10 non-real roots. And that's kind of how the roots work and what they look like a little bit more. Again, so you're looking for hills or valleys in this section that are off the x-axis. So a turning point that happens above the x-axis like these. 1, 2, 3, and 4 in that case that were off. 1, 2 in this case, because this one over here that you might see here is actually covered by this. And then notice all 10 of those. So that's how that works.